Hello students, let us discuss MOT diagram, that is molecular orbital diagram. So in this video, we are going to discuss how to make a molecular orbital diagram, and we're going to discuss about the molecular orbital diagram for the different molecules. This is the molecular orbital diagram for the molecules boron, carbon, nitrogen and the molecules before boron. So let us discuss first this diagram. This is an energy level diagram. That means from lower energy to higher energy. So the orbitals which have lower energy should be made below, and the orbitals which have higher energy it made above. So as we have learned that atoms combines to form molecule. That means atomic orbital combines to form molecular orbital. So we'll be writing the atomic orbital in the two side and molecular orbital we are writing in the center. So what it shows? Atomic orbital combines to form molecular orbital. As we have learned in the linear combination of atomic orbital, the atomic orbitals combines to form molecular orbital, that is sigma 1s, that is a bonding molecular orbital, and antibonding molecular orbital. So first of all, we know that atomic orbitals are the energies according to the energy. First we'll be doing the filling of 1s, then 2s, then 2p. Now why we have made 1s down? Because the energy when you compare with 2s, 1s is less. Therefore first we have to make for 1s because it's an energy level diagram. First for 1s, then for 2s, then for 2p. We have to keep the order because it's an energy level diagram. So after 1s only you have to make up 2s, then up 2p. So this is for this atomic orbital. Now for another atom, because two atoms are combining, for another atom this side we are making, that is this is on the left hand side, this is on the right hand side. So the two atomic orbitals, that is on the left hand side one atom, right hand side representing another atom. So we are making in this way. So again 1s, then 2s, then 2p. So this is we have learned for atomic orbitals. And why we are making 2p, the three boxes? Because it is p and all the energies, that is 2px, 2py and 2pz, all these have same energy, so we'll be making on the same line. So because it's an energy level diagram. Now what about the molecular orbital? We know that atomic orbital combines to form two type of molecular orbital, that is bonding molecular orbital and antibonding molecular orbital. So that is represented here in two boxes. As we have learned 1s and 1s combination. What is 1s combination? 1s plus 1s, that is 1s plus and minus give rise to sigma 1s plus and sigma star 1s. So this we have already learned. So this is bonding molecular orbital, this is antibonding molecular orbital. So we'll be making sigma 1s, that is bonding molecular orbital, sigma star 1s, that is antibonding molecular orbital. As we have learned that the energy of sigma 1s, that is bonding, is less, and the energy of antibonding molecular orbital is greater. So now it is clear why it is sigma 1 is made down and why sigma star 1s is made up. That is, in compared to the energy of 1s, sigma 1s have lower energy, therefore we have to make little bit down, and the energy of sigma star is little bit greater, so we have to make little bit up in compared to 1s. So this is about 1s. Similarly 2s plus 2s. What is that combination, linear combination? That is 2s plus and minus 2s, that is a combination of 2s orbital, atomic orbital, give rise to sigma 2s and sigma star 2s. So that is bonding molecular orbital and this is antibonding molecular orbital. So two molecular orbitals are formed, bonding and antibonding. Antibonding we are representing in stars. So that is we are drawn here 2s plus 2s combination, that is combination of 2s and 2s give rise to bonding molecular orbital and antibonding molecular orbital. So that we have made here in the form of box, that is sigma 2s and sigma star 2s, that is bonding and antibonding. The energy of bonding is slightly lesser, therefore we are making little bit downer, and the energy of antibonding molecular orbital is slightly greater than 2s, therefore you have to make little bit up. So this is for 2s. But in the case of 2p, 1, 2, 3, that is 2px, 2py, 2pz. Here also 2px, 2py, 2pz. As we have learnt in the linear conditions for linear combination of atomic orbital, they should have same energy and same symmetry. That means 2pz plus and minus 2pz, that is giving rise to which type of combination is taking place here? It is a head to head. So sigma 2pz, that is bonding. This is bonding molecular orbital, and what is formed here? That is sigma star 2pz, that is antibonding molecular orbital. So from 2px, 2py, 2pz, 2pz forms which type of molecular orbital? That is sigma 2pz and sigma star 2pz. So we'll be making here sigma 2pz, and here you can see sigma 2pz. But 2px and 2py, it forms pi because there is a sidewise overlapping in the case of 2px and 2px. So we can say that it results in the formation of pi 2px and pi 2px and pi 2p star x, that is bonding and antibonding. So in this case we need to make a pi. You can see pi 2px and pi star 2px. Now here the question arises, why we have made two boxes here? Because the study is shown that energy of pi 2px and pi 2py is same. This one is pi 2px, this one is pi 2py. So when you see the energies which is shown here, you can see the energy of pi 2px is equal to energy of pi 2py. Therefore, these two should be made together. Like, why we making two boxes here? Because the energy of pi 2px and pi 2py are same. Similarly, the energy of pi star 2px, that you can say here, the energy of pi star 2px is equal to the energy of pi star 2py. So that's why we have to make two boxes together, because their energy is same. But energy, when you compare with the sigma 2pz and with the pi 2px and pi 2py, there is a different energy. So this is the correct way. You have to make the two boxes first, then one box, then two box, one box. These two boxes, these two boxes are the bonding molecular orbital, and these two are the antibonding molecular orbital. First of all, you need to remember bonding molecular orbital. This is bonding molecular orbital which have lower energy, therefore you have made little bit down. This is the level of energy of 2p. So the energy of bonding molecular orbital is little bit lower, so you have to make little bit down. The energy of antibonding molecular orbital is little bit higher, so you have to make little bit up. And When you are making this diagram, try to learn the simple way to, because these two are okay, you can easily make these two. But when you're making for 2p, learn the sequence. Here you have made two boxes. So 2, here you have made single box 1, here you have made two box 2, here 1. So this is the simplest method I am telling to remember the diagram. So how we'll be making the diagram for 2p, 2p give rise to the boxes you have to make 2 1 2 1. So what number you need to remember? It's a trick to remember this one, 2 1 2 1. That is for which molecule? That is for boron, carbon and nitrogen. You have to follow this number. Which is that number? 2121. That is 2121 number you can remember. It's not any scientific concept here. It is only a trick. It is a trick to remember the diagram for these molecules. That is 2121. What is that 2121? 2 box, 1 box, 2 box, 1 box. That you have to make for this diagram. That is for boron, carbon and nitrogen. But you need to remember that 2 box means pi 2px and pi 2py. Single box means sigma 2pz. Again 2 box here, that is representing pi star 2px. That is this box, and this box is pi star 2py, and this single is representing sigma. So single box represent sigma 2p z, and 2 box represent that is pi 2p x and pi 2p y. That you need to remember here. So that is the diagram, that is a molecular orbital diagram for these molecules. For oxygen, fluorine and neon, the diagram till here it is same as we have learned for the case of boron, carbon and nitrogen molecule. Till here it is same, everything is same. But the 2p part, this is different. That you need to remember here. In this case, the energy of sigma 2pz. Here is only the difference. You can, when you compare it, here is only the difference. So there we have learned the number 2121. So here you will be learning the number that is 1221. So what is the difference here? Because here the energy, here the energy get varied. That is the energy of pi 2px and pi 2py when it is compared with sigma 2pz. Sigma 2pz have lower energy than this. So here is only the variation. Here is only the variation. So till here everything is same. That is here, and the rest of the part is same as it is. Only the difference is in this part. That is this part. So here are the two diagrams we have discussed. Now let us just compare these two diagrams so that it will be easy to remember the diagram. In this you can compare the two diagrams. The two diagrams which we have learned, that is for boron, carbon, nitrogen, this diagram, oxygen, fluorine and neon, you have to take this diagram. Now just compare these two. You can see whatever things are similar. Till here everything is same. That means when you are making the diagram, this much part is same. You can see these part are same. So where is actually the difference? And here also you can see it is same as it is. This part is also as it is same. You can see it is same. But where is the difference? The difference is in this part. This part is different. You can see we can compare the two diagrams here. So which part is the different? That is the energy of sigma 2pz and pi 2px and pi 2py. There is a variation in the energy. So that is most important here. So I told you to remember the trick. I told you to learn a trick that will be easy to remember this concept. That is, here I told you 2 1 2 1. The number 2121 representing, that is how many boxes you should need to make. That is 2 box here, 1 box here, 2 1. So I told you to learn the number 2121 for the case of which molecule? That is for this molecule. But in the other case, here you can see 1 box. That is 1 box, 2 box, 2 box, 1 box. So that is the number 1 2 2 1. So this you need to remember. Here is the difference. That is, this is the difference. So that you need to remember. That is 2121 for here, and here it is 1221. That you need to remember. 2121 and 1221. This is only the trick. I told you it's only the trick to remember this diagram. So let us do some problems. How we'll be making the molecular orbital diagram for each cases, because here we have made only the empty boxes. Now we have to fill the electrons in that. So that we'll be going to do here. So let us do one or two some examples we are doing here. How to fill electrons, that we have to discuss here. So in this you need to follow all the 3 rules which we have already discussed for the atomic orbital. That is Abba principle, Pauli exclusion principle, Hund's rule. We have to follow these 3 rules here also. That is filling of molecular orbitals. So first we'll be starting with the simplest molecule, that is hydrogen molecule. Hydrogen means H2. Hydrogen molecule, that is, we know that H plus H give rise to H2. That is, hydrogen atom combines to form hydrogen molecule. So on the left hand side and right hand side, we'll be making the atomic orbital. So this is the atomic orbital for hydrogen. For one hydrogen, this is the atomic orbital of another hydrogen atom. As we know that only there is one single electron in the hydrogen. So that is in the 1s. So we'll be making 1s and 1s. And since there is only single electron in 1s, so we'll be making single electron here, single electron here. First you make the left hand side and right hand side. Now we have to fill the center part. Center part is the molecular orbital. So one electron is here, that is this electron. One electron is here. Now 1 plus 1, how much? 2. Now we have 2 electrons. So you have to fill in the order, that is from lower energy to higher energy. You have to follow, and you have to follow all the 3 rules, that is Abba principle, Pauli exclusion principle, Hund's rule. So we are filling here. Already it is filled in this, but still I am making here. So 2 electrons are there. So first electron, second electron should not go up. Why? Because according to the rule, first you have to fill the lower energy orbital, then only fill the higher. And one orbital maximum 2 can accommodate. So after one electron, the second electron will be here itself. So now total 2 electrons are there, and both the electrons are filled in sigma 1s. So what will be the configuration for this one? That is the electronic configuration for this molecule. For this you have to write the molecular orbitals. So sigma 1s. Sigma 1s, this you can see electronic configuration, sigma 1s. Since here 2 electrons are there, so you have to write 2 here. So that is sigma 1s2. This is the electronic configuration for which molecule? Hydrogen molecule. Now with this diagram we can able to find out the bond order. How we find out bond order? That is the number of electrons in the bonding molecular orbital, that is this, and the number of electron in the minus antibonding molecular orbital. Bonding molecular orbital, as I told you, the orbital which is representing without star, that is the lower one. This is bonding molecular orbital and this one is antibonding molecular orbital. So how many number of electrons are there in bonding? You can see 2 electrons are there. So what is NB now? NB is 2 because 2 electrons are there in the bonding molecular orbital. That is represented NB. Na represented the electrons in the antibonding molecular orbital, that is Na. A represent antibonding molecular orbital. So when you check here in the antibonding molecular orbital, how many electrons are there in this? There is no electron. So that's why we are writing 0 here. So that is Nb minus Na, that is equal to 2 minus 0, and this you have to divide by 2, so that is equal to 1. So what is the bond order? Bond order means the number of bond present between the two hydrogen atom, because here we are talking about hydrogen molecule. So that is single bond. One bond is present because the bonding order we have calculated here, that is equal to 1. So it means a single bond is present between the two hydrogen atom. So in this diagram we have find it out the bond order. From this diagram we can compare its magnetic behavior also. We can compare, we can find out its magnetic behavior. When all electrons are paired in molecular orbital, then it is called as diamagnetic, and if it is any unpaired electron is there, then it is paramagnetic. So in this case, you can see in the bonding molecular orbital the electrons are paired. Paired means you can see in a single box 2 electrons are there, that is paired electron. So we can say that the magnetic property, it is diamagnetic because it is paired, therefore it is diamagnetic. So this is the molecular orbital diagram for hydrogen molecule, its electronic configuration, that is, this is the electronic configuration for this molecule, this is the diagram for this molecule, and this is the bond order we have calculated, and we also find out its magnetic behavior, that is diamagnetic. Next, helium molecule. In the same way, we will be making helium atom combines to form helium molecule. As we have already learned the electronic configuration for the different elements for helium. What is the electronic configuration? 2 electrons are there, that is 1s2. So this is the electronic configuration of this helium atom, that is 1s2 here, and for this helium atom 1s2. So first we are making on the left side one helium atom, right side another helium atom. 1s2, so in here the 2 electrons, here they are the 2 electrons. So when we are making for helium molecule, 1s plus 1s combine to form sigma 1s and sigma star 1s. That is bonding and antibonding molecular orbital. Now we'll be started the filling of electrons in this, because already it is filled in this one, but still I will making here. So since here 2 electrons are there, 1, 2. Here also 2 electrons are there, 1, 2. Now count the 2 numbers, 2 plus 2, 4. So we have 4 electrons. So that we need to fill. So total 4 electrons start from lower one. So that is 1, 2. 3 will be up. That is 3, 4. So total 4 electrons are there. So that is over. 4 electrons we have filled. So how we have filled? That is 2 electron is here, 2 electron is here. So total 4. 1, you have to see the order how it is I am filling. You have to go in the same manner. 1, after that 2 here itself. Third will be up and the fourth one here. So the total 4 electrons, it is filled in this way. Now this is the diagram for helium molecule, MOT diagram for helium molecule. Electronic configuration, this is sigma 1s. So how many electrons are there? 2 electrons are there. So we have to write sigma 1s 2. Next, this is sigma star 1s. How many electrons are there? 2 electrons are there. So sigma star 1s 2. So this is the electronic configuration for helium molecule, that is sigma 1s square and sigma star 1s2. So this is the electronic configuration for molecule. Which molecule? Helium molecule. Now when we find it out, the bond order, bonding electrons, how many number of electrons? This is the bonding molecular orbital and this is antibonding molecular orbital. So count how many bonding electrons are there. That is 2. 2 are bonding molecular orbitals having 2 electrons. So we will be making 2. So what is NB? 2. What is Na? Here 2 electrons are there, that is 2. So 2 minus 2, that is equal to 0. That means between the two helium atom no bond exists. What is bond order? The number of bond present between the two atom in a molecule. So in the case of helium, no such bond exists between the two helium atom because the bond order is equal to 0. Therefore we can say that such type of molecule does not exist because it is not in the molecule form. Helium exists in the atomic form, that is monoatomic form. So that is, we can say that if the question is asked why helium molecule does not exist, so you need to make the diagram, this one, and you have to show that its bond order is equal to 0, therefore it does not exist. So it is one of the textbook question also. Next we'll be trying for lithium molecule. Atomic number for lithium is 3. So what is the configuration? That is 1s2, that it is written here 1s2 and 2s1. This is the configuration for lithium atom. Similarly, another lithium atom is also there. Configuration, electronic configuration 1s2, 2s1. So that is the filling of atomic orbital. Now we will be filling the molecular orbitals. So we have to follow the same method what we have done by using the above principle, Pauli exclusion principle, Hund's rule. We have to do the filling. So already it is filled, but still I am making in order to make this concept clear. Here 2 electrons are there because 1s2. Here also 2 electrons are there because 1s2 for lithium atom. 2 electron here, 2 electron here. So total 4 electron. So we'll be having 4 electron total. So start the filling of molecular orbital. Start from the bottom one. That is 1, 2. Then 3, 4. So it's over. 4 electron over. So that is the filling of sigma 1s and sigma star 1s. Now we'll be doing for 2s. 2s, here there is only single electrons are there in the 2s atomic orbital for the lithium atom. So 1, 1, 2 electrons. So we'll be starting here 1, 2. That is the second electron. Only 2 electrons are there that we have filled here. So this is the filling. Now there is no electron for sigma star 2s. Now when you check the number of electrons here 1, 2, 3, 4, 5, 6. That is 6 electrons. That is these 2, this 2 and this 2. So total 6 electrons are there in the molecular orbital. What is the atomic number for lithium? For atomic number for lithium is 3. But for lithium molecules, 3 electrons in lithium atom. So 2 lithium atoms are there. So equal to 6. So you can compare 6 electron here, 6 electron here. So you can compare like this also. So when you write the electronic configuration for lithium molecule, that is sigma, start from the lower one, sigma 1s. This is sigma 1s. 2 electrons are there. Sigma 1s 2. Sigma star 1s 2. And sigma 2s 2. So this is when you count the number of electron here, 2 plus 2 plus 2, 6. Here also you are getting 6. So that is, you can check here. Here the sum of these is 6. That is 6. And when you make the sum of these, it is getting 6. And for lithium molecule, total number of electron, one lithium atom have 3 electrons. So 2 will having 3 plus 3 equal to 6. So in all these way we are getting the total number of electron 6. When you do the bond order, how you find out bond order? Nb minus Na. That is the bonding molecular orbital electron minus antibonding molecular orbital electron divided by 2. So better count the number of electron in the without star and count it in with star. That is sigma 1s. This is bonding. So 2 electron here, 2 electron here. So 4 electron we have this. So 4 minus and 2 electrons. That is this. This is antibonding molecular orbital. So what we can say, that is 2 here. So 4 minus 2 divided by 2 is equal to 1. So what is the bonding or bond order here? That is 1 is the bond order. What about the magnetic property? You can check here. This is paired, this is paired, this is paired. You have to check the molecular orbitals, not the atomic orbital. So when you check the molecular orbitals, all electrons, all orbitals are paired. So we can say that it is dimagnetic. So this is the MOT diagram for lithium, its electronic configuration, bond order and magnetic property, that is dimagnetic. Next one, that is boron molecule B2. We have to make the MOT diagram for B2. So I told you, you have to learn the trick which I told you, that is 2121 is for boron, carbon and nitrogen. So we are making for boron. So you have to make this diagram in which 2121, because till here I told you it is same. So where is the difference here? The difference area is this area. That is 2 here, box, 2 box here, 1 box here and 2 box, 1 box. That's why I told you learn the sequence 2121. This is the trick to remember the making of boxes here. So let us do for this one here. First of all, boron. Boron, this is the 2 boron and this is for B2, for boron molecule. First of all, we need to write the electronic configuration of boron. Boron atomic number. What is the atomic number? That is 5. Hydrogen, helium, lithium, barium, boron. 5. So let us do first write the electronic configuration, that is 1s2, 2s2 and 2p1. So this is the electronic configuration for boron. Similarly, we will be making for this filling of atomic orbital, we will be doing for other boron, that is 1s2, 2s2, 2p1. So this is the filling of the boron atoms. Now we will be doing the filling of molecular orbitals. So we have to do in the same order how we have done for others also. Count the number of electron, that is 1, 2 electron here, 2 electron here. So total 4. So we'll be starting from down 1, 2, 3, 4. Now it's over. Now we'll move into the 2s. 1, 2 electron here, 2 electron here. So total 4. 1, 2, then 3, 4. This is over. Now we'll be doing the filling of 2p. So 2p, single electron here, single electron. So total 2 electrons we have here. Now the question arises, from where we start the filling? That is from the lower one, that is having lower energy. When you compare here, which one have lower energy? This have lower energy. But here pi 2px and pi 2py, that is both have the same energy. That's why made together. So we need to follow the rule. When they have a same energy, first it should be singly occupied and then only we have to do pairing. So 1 electron here, 1 electron here. That is 1 electron in pi 2px, 1 electron in pi 2py. Since there is only 2 electrons are there, so this is over. So that is enough filling because only 2 electrons are there. So here single electron in pi 2px and single electron in pi 2py. So when you check the electronic configuration, so till here, till 2s, that is from till here it is same as it is electronic configuration how we have done for the till we have done for lithium and all, it is same. Now what is the difference here? Next, this part, that is pi 2px. Pi 2px have 1 electron and pi 2py have 1 electron. Why? Because when you check here, here there is a single electron, here there is a single electron in pi 2px and pi 2py. Therefore, pi 2px1, pi 2py1. So this is the electronic configuration of this molecule, that is B2 molecule. When you find out the bond order, Nb minus Na divided by 2. What is Nb? Count the number of electron, that is here 2, here 2, 2, 6. Bonding means which is without star, that is bonding. Which orbital, molecular orbital is starred, that is antibonding. So bonding, so 2 electron is here, 2 electron is here and 2 electron here. So total 6 electrons. So 6 minus, which one is the antibonding molecular orbital? That is this one. This is antibonding and this one is antibonding. I am using the different colors. You can see bonding molecular orbital electrons are represented in yellow color, and the pink color which I am showing, that is antibonding. So you can see 2 electrons here, 2 electrons here, 4. So 6 minus 4 divided by 2 is equal to 1. Therefore, the bond order is equal to 1. What about the magnetic property? When you check this one, here you can see, that is this 2. Here you can see there are single electrons. Therefore, it is paramagnetic. If any single unpaired electron is there, then it is paramagnetic. So this is the diagram, MOT diagram for boron. Its bond order 1. That is for boron molecule, bond order equal to 1, and the magnetic behavior is paramagnetic. Next, carbon molecule, that is for C2. We are making MOT diagram for C2. First of all, we need to write down the electronic configuration, atomic number 6. So 1s2, 2s2, 2p2. So that we have to write like this, and this is also carbon. So atomic orbital carbon 1s2, 2s2, 2p2. So these are the, we have done the filling of atomic orbital. Now we will be filling the, that is molecular orbitals we are going to fill. So molecular orbitals, you have to make the sum of this 1, 2, 3, 4. So 4 electron. So like this you have to fill. Now 2s, also 2 to 4 electrons are there. So 1, 2, 3, 4. What about 2p? In 2p, here 1, 2 electron, here 1, 2. So total 4 electrons are there. Now here when you check here, pi 2px and pi 2py are there, which have same energy. So according to the rule, first should be given single, then do the pairing. So total 4 electrons here and here, total 4 electrons are there. So 1, 2, then 3, then 4. You have to fill in this way. It is not exactly getting into that box, but make it sure that when you are writing, at least you make that electrons in that box. So this is we have done the filling of electron in the molecular orbital. So now we will be writing the electronic configuration, that is electronic configuration here sigma 1s. So 2 electrons are there, so sigma 1s 2. Then here sigma star, this one is sigma 1s, so sigma 1s square, sigma star 1s square, then sigma 2s square, then here sigma star 2s square. And in the case of pi 2px and pi 2py, there are 2 electrons, and they have same energy, these orbitals. So pi 2p x square, pi 2py square. So this is the electronic configuration for this. How you find out the bond order? Nb minus Na by divided by 2. Nb, which electrons are Nb here? So let us mark, this one is bonding molecular orbital, this one is bonding molecular orbital, and this one is also bonding molecular orbital. So total how much electrons are there? Count it. So 2, 4, 6, 8. So total 8. So bonding molecular orbital, 8 electrons are there. What about antibonding molecular orbital? For antibonding molecular orbital, when you count it here, this is antibonding molecular orbital and this is also antibonding molecular orbital. So total 4 electrons. Count the number of electrons here, 4. So that is 8 minus 4, that divided by 2, which is equal to 2. So it shows that it having bond order 2. What about the magnetic properties? Because all the electrons are paired in the molecular orbital, that you can check here in the molecular orbital, all electrons are paired. So therefore it is dimagnetic. So this is the MOT diagram for this molecule, that is C2. Next molecule, that is O2, oxygen molecule. Oxygen molecule, we will be making the diagram, and remember the sequence I told you. For oxygen, fluorine and neon, we have to make this molecular orbital, in which I told you to remember the trick. That is, what is that trick here? That is 1, 1, 2, 2, 1. For oxygen, fluorine and neon, that is 1 box, 2 box, then 2 box, 1 box. So you have to make this molecular orbital first in this way. Next, let us do the filling electronic configuration. First we will be writing for oxygen atom, that is 1s2, 2s2, then how much electrons remaining? So atomic number 8. So 4 electrons are remaining, that is 2p4, 1, 2, 3, 4, 2p4. Similarly, here also we are doing, that is 2 electron here, 1s2, 2s2, 2p4, that is 1, 2, 3, 4, 2p4. Now we will be filling the molecular orbitals. So 1s and 2s already we have done it in the other molecules. So I am directly writing these. Okay. Now about the 2p electrons. So total how much electrons are there in 2p? That is 4 electrons are here and 4 electrons are here. So total 8 electrons. So let us do the filling of this one, 8 electron. So 1 will be here, 1, 2. Then where will be the third one? 3 here, 4, then 5, then 6, then 7, 8. So this is the correct way of filling. You have to follow the rules, that is above principle, Pauli exclusion principle, Hund's rule. So you can see that in pi star 2px and pi star 2py, you can see single electrons are there. So then we can say it is paramagnetic. Other all are paired. All are paired, only these two, that is pi star 2px and pi star 2py, there is a single electron in these. So it is we can call it as a paramagnetic. Only look at the molecular orbital, not the atomic orbital. Next, electronic configuration. The same way you can do it, electronic configuration. So what you are getting here, last electron, that is in pi star 2px and pi star 2py, you can see single electrons are there, that is represented here. So till here we have already discussed. So this is the electronic configuration for oxygen. What about bond order? That is when you find it out, the electrons, that is bonding molecular orbital electrons and antibonding molecular orbital, that is I am marking this one, this is bonding molecular orbital, that is NB. So these are the NBs. These are the NB. So total how much electrons are there? When you count it, it is equal to 6 here, 7, 8, 9, 10. So 10 electrons are that is bonding molecular orbital electron. Antibonding molecular orbital, how much electrons are there? That I will mark with different color. This is antibonding molecular orbital, this one also, and this one also. So count the number of electron in this that I marked with violet color. That is the antibonding molecular orbital, which is represented in star. So 2 here, then 2 here, 4, 5, 6. So 6 electrons, therefore Na is 6. So 10 minus 6 divided by 2 is equal to 2. So that is the bond order we are getting 2 here for oxygen molecule. That we are already familiar that there is 2 bond between the 2 oxygen atoms in the oxygen molecule. So this is about the oxygen molecule. Similarly, you can do for fluorine and neon. The diagram will be the same, but filling of electron will be different. Let us do a comparative study about the molecular orbital diagram for the different molecule, which is given in the textbook here. That is for boron, carbon, nitrogen, oxygen, fluorine and neon it is given. So as it is given in the 2 sections here. So I told you 2 diagrams are there. For boron, carbon, nitrogen, I told you to remember the number 2121. That is 2. This is 2 box, 1 box, 2 box, 1 box. But for oxygen, fluorine and neon, you have to remember the number, that is 1. This is 1 box, 2 box, 2 box, 1 box. So 1, 2, 2, 1. I told you it's only a trick to remember the diagram. Otherwise you will get confused that which diagram is correct. And when you compare here the electrons, the filling of electrons is shown, and the outer valence electronic configuration is also given here. Okay, and the bond order is also given. When you compare the bond order, look at the bond order. 1 for boron, 2 for carbon molecule, that is all for molecules, and 3 for nitrogen molecule. Then again oxygen 2, then it become 1, then it becomes 0. So comparatively if you want to study, you can study in this way. So all of you make the molecular orbital diagram from hydrogen to neon. That is important. All have to make the diagram, and not in this way, the way how I told you to make the diagram. You have to make the diagram for each element, for each molecule, that is from hydrogen to till neon. From hydrogen to neon, you have to make MOT diagram for the molecules, and you need to write down the electronic configuration, bond order, and also the paramagnetic or diamagnetic. You have to find it out for each. It's very important. This is, you need to practice it. So all of you do this one in your notebook. So this we have discussed about the molecular orbital diagram for the different molecules, in which we have discussed some of the examples. The rest of the examples you have to try by yourself and check your answer with a textbook, in which it is given in the comparative way. So this is all about this video. Have a nice day.